So thanks for joining. I'm Scott Schultz. I'm one of the managers at Mellanox. One of my tasks is HPC and more recently AI. So I manage all of the AI activities. I'm also a board member here with an OpenPOWER and very active in the technical steering committee and whatnot from the power side. So really, what I wanted to begin this talk on was around. As far as interconnect technology and how it applies to OpenPOWER, HPC, and AI. So really, in order to ensure the highest performance for a diverse set of workloads, it's really important to understand how data is used and how it really coexists in similar environments, right? So high-performance computing, AI, and big data really have very similar underlying hardware needs. Especially when it comes to the networking requirements, and it's really important to. It's all about the ability to store the data and move the data, and to exchange messages and even the computed results, right, of thousands of parallel tasks. And have that done fast enough in order to keep the compute resources busy and running at peak efficiency. And this is really where Mellanox plays an important role. So with key offloads, which we'll go into, GPU Direct, our RDMA, Sharp is one of the topics that we'll talk about. These types of things are now becoming the de facto standard when it comes to these widely adopted technologies that are being deployed today. So now, not to forget about the number one system in China, but Mellanox is also connecting the number one systems all around the world. So today, alongside the U.S. leadership systems that are on track, the Summit and Sierra systems that are going to be deployed here shortly, as well as the fastest supercomputer in Japan, and the one from Skynet in Canada. And what's interesting about this system as well is that it's being deployed with Dragonfly Plus, which is one of the newest topologies from Mellanox. And what's interesting there is you're able to achieve a greater amount of efficiency and very similar performance of that of a native fat tree topology, but really in a much more cost-effective way. And so we believe that Dragonfly Plus is going to be more pervasive as we move into 200 and 400 and beyond as far as the network is concerned. So this year really is already proven to be a huge game changer in the next generation of performance, right, for both HPC as well as AI. And the race continues to be around solving the challenges of not only the traditional HPC workloads, but also for scalable deep learning. And keep in mind that most of the almost all of the most popular deep learning frameworks today can scale to multiple GPUs within a server. That's really not a problem. Really, what the challenge is it's more difficult to scale to multiple servers, each having multiple GPUs. And so we have, and the challenge in particular is precisely where Mellanox has been the clear leader as the only interconnect solution needed to be able to deliver the needed performance around AI and HPC. So, we have a complete end-to-end solution of intelligent network endpoints, switches, and cables. And really, it's the most reliable and the most suitable interconnect for the power architecture. So today, data growth remains the biggest challenge in today's data center infrastructures. And while there are many sources that predict exponential growth of this data out to 2020 and beyond, they all are really much in broad agreement that the size of the digital universe is going to double, right, almost every 2 years. So storage, data movement, and the complexity of keeping the data secure is these are really key challenges for any data center. Now, here's a couple of really interesting examples of how much data is really being generated today. And when I mean big data, I mean really big data, right? So if you take a look at these two examples, These are fascinating examples when you think about one Pratt and Whitney engine being able to generate up to 844 terabytes of data on a 12-hour flight. That's a lot of data. But also keep in mind that today even most companies that are based in the U.S. have at least about 100 terabytes of data, right? And if you take a look at NASDAQ or the New York Stock Exchange in particular, right, they actually capture more than a terabyte of data every single trading day, right? Every trading session. So it's really an amazing amount of data that we're going to be able to rip through and process, and the network really is critical from moving the data from point A to point B. So this is just a very simple kind of slide that basically says, hey, well, you know what? Okay, the network's important, but really, what is important? Why is not bandwidth just the only thing that you're thinking about? So really what's important for machine learning and big data, it's listed right here, right? So, high bandwidth and low latency. And, there's, from a Mellanox perspective, we have both InfiniBand as well as Ethernet. So depending on the infrastructure, you're always going to get better performance with InfiniBand, quite honestly, because our switches actually have less than 90 nanoseconds of port-to-port latency. But even on the Ethernet side, if you're thinking about moving data using RDMA over converged Ethernet and taking advantage of all the acceleration offload engines there, right? Spectrum is one of the world's lowest latency Ethernet switches available. So the port latency there is less than, I think, 300 nanoseconds. So Spectrum was also designed around zero packet loss, right? So in the world of RDMA, right, it's very critical. And basically, the rules of engagement there says the packets must arrive in order. And on the Ethernet side, that's really a challenge. So Spectrum is very well balanced in nature to be able to be a zero packet loss switch, being able to deliver packets in order with very infrequent a packet drop, if ever. But mostly, I think most important is around these. It's all about the native offload. So RDMA, GPU Direct RDMA, and I'll cover those in just a few minutes. People are moving to containers, so support for virtualization and containers is very critical. But also, I'm going to highlight and talk about Sharp, which is our approach to what is called in-network computing. And then, of course, the storage acceleration, right? So, RDMA and NVMe over fabrics is beginning to take off, and storage acceleration is very important, as well as security. Okay, so really our approach to solving some of the key bottlenecks in terms of moving data is actually working on the data as it traverses the network. So, by introducing this notion of intelligent co-processing capabilities into the network reduces communication latencies by an order of magnitude, right? So, and that really results in exceptional performance to the application for not only traditional HPC, but also for the new workloads around AI and deep learning. And really, when I talk about some of the core features of the interconnect today, right? It's not just a network that just moves data. Sharp gives you the ability to move to compute data as it traverses the network. So instead of having to move it from one endpoint to another and then start working on the data, right? We start working on the data as it moves through the network. MPI this is an example of working on the data in the endpoints. So we're able to now move more collectives and more MPI operations, not only onto the switches, but we're able to handle things like MPI at the endpoint. All right, so being able to do tag matching in hardware results in more than 35x performance improvement when you're talking about traditional HPC and MPI workloads. So we also have this notion of shield, which is quite interesting in the sense that it allows you to recover from let's say you're doing maintenance or you pull a cable or a port goes down or something like that, right? We're able to actually use communication techniques within the network to notify the switches that, hey, there's a problem, and make immediate changes into the path in which the data movement is taken. And so that really is turns the network into, or the Mellanox network in particular, into a very robust type of self-healing capable network. And then I'll talk a little bit more to GPU Direct RDMA, and thanks for being here, because I know DK Panda is talking about his MVAP pitch over in the other room as we speak. So, like I mentioned, InfiniBand delivers the best return on investment, and it really is awesome to be able to take a look at a technology that can give you out of the box about 2.5x times better performance than any of the competitive solutions. And it's easy to see here why Mellanox has always been the de facto standard when it comes to high performance computing, especially for weather codes and automotive and chemistry, right? And these are not just Mellanox numbers. Right? These are customer numbers that real customers have actually achieved and said, you know what, thankfully we're able to just put in the Mellanox interconnect, and it just works out of the box. And for codes like WRF, this is the performance that we're getting. So, but also we can unlock better performance for AI, not only from a performance perspective, but also from a scalability perspective, right? Getting these boxes, or getting the algorithms to move outside of just the single fat box, right? So distributed AI is really the wave of the future, and I'm going to spend a little bit more time talking to this. And today, nearly every leading machine learning framework actually is natively enabled with Mellanox accelerations under the hood. So being able to take advantage of RDMA, GPU Direct RDMA, and these types of things are key to reduce the training times and actually increase accuracies in a much reduced time. So being able to start a model training before leaving at the end of the day, right, and having those results there for you early in the morning, really this is the game changer for the data scientist. And so when we talk to the types of performance that we're talking about, GPU Direct is one of them in particular that has been around for many years now, and it's really more optimized than ever. And if you take a look, right, moving data from one GPU to a remote GPU in a different compute node across the fabric no longer requires the CPU to be involved in the movement of that data. And so that really reduces your latencies by 10x. So what used to take you more than 19 to 20 microseconds to move a message from point A to point B now takes you well under 2. And so GPU Direct really was purpose built for things like deep learning, and really gives you the ultimate in lowest latency communications across any acceleration devices, but in particular GPUs. Now, there's also a newer version of GPU Direct called Async. And in the previous slide, and you can see that the data path is basically what's being offloaded here. The control path is not, right? So the CUDA threads are launched, and the CPU still needs to manage those threads and those kernels. And so the CPU is somewhat still involved. But with GPU Direct Async, we're not only removing the data path from CPU involvement, but we're also removing the control path. So now what you'll basically will be able to launch batches of kernels from CUDA, and we're giving all the control of the network basically over to the GPU. And so, excuse me. So as both the data path and the control path go directly between the GPU and the Mellanox interconnect, that really allows for several things. In particular, you'd be able to fundamentally use a much lower cost, lower power, and slower clocked CPU. Actually, that's one of the biggest benefits. But we believe that that this is going to give even better performance than just by offloading the data path alone. Now, this is available already today. It is one of the features. I think it's supported in Mellanox OFED today, so you can always take a look at it. And then what I wanted to do is talk a little bit around the notion of distributed training. And training on large data sets can take a really, really long time, right? And so in many cases, the training has to happen very frequently. And as you know, and the notion is as you add more workers, it's going to actually reduce your training time. And hopefully, you know, accuracy is not affected by that whatsoever. And really, data parallelism is the solution. And when you talk to model parallelism, right? In some cases, the model doesn't even fit into compute, right? So you know, if you had a smaller compute engine or something like an FPGA, right, the model won't even fit. And so here, networking really does become a critical element. And in particular, the high bandwidth and low latency and RDMA are almost mandatory when you move into this type of model parallelism. So, so I understand you had a little bit of interest in Sharp and how it's going to help you with your AI models. So, so one of the key elements of using this network as a coprocessor is with what is called Sharp, and Sharp being a is really a reliable, scalable, general-purpose type of design, which makes in-network tree-based algorithm mechanisms. And today it's already used and deployed in HPC installations. In particular, like you mentioned for the Coral deployments and whatnot. These are based on the switch IB2, which is a 100 gig infrastructure. This type of in-network computing manages and executes these MPI operations very seamlessly from the switches, but are very much now today geared towards the smaller message sizes. And so with our upcoming quantum-based switches and 200 gigabit technology, then basically what we're able to do is very similar operations and spend all reduced being the primary collective for AI that's most important. We're able to actually handle up to a 2 gigabyte message size at wire speed, right? And so basically, you know, Sharp can perform these high collective operations, not only, of course, you know, all reduce, which is very important for AI, but barrier, reduce, you know, broadcast. These are other collectives that are already supported in the switches. And when I said that we actually manipulate and we can actually work on the data, right? The actual switches themselves have the ability to perform sum and min and max and you know, OR and XOR and these types of operations on the data. So that's the concept and the notion behind Sharp. And this is one example, right, of being able to show you the performance of how it's basically done today, or how you can do it within the network using the Mellanox switches. Right, so this shows you fundamentally that as you add more compute infrastructure to these parallel communications, right, the latency remains very flat, and that's a good sign of being able to show how scalable a network is. So if you're doing it in software today, right, you can see that the latency goes up as you continue to add more compute elements. So that's a kind of a non-scalable type of approach. It is some approach, so we believe that Sharp is really a game changer in the fact that you can enable about a 75% reduction in latency, and really keep that latency very flat. This is a kind of an animated slide of fundamentally how Sharp will influence the AI, the distributed model, right? Instead of having a parallel a parameter server, basically Sharp will replace the need for an external parameter server. And where you once used that parameter server, right, to perform maybe the gradient averaging, Sharp actually removes the physical server completely, right, and actually reduces the amount of data that has to traverse the network. So we believe that, for AI and deep learning, Sharp is going to be a very significant technology and a game changer when it comes to performance and whatnot for these types of workloads. Now these I'm just going to go through a few samples, and then we'll be able to wrap up and maybe take a few questions. This is TensorFlow, some of the initial work that was done. I mentioned that most of the frameworks, TensorFlow and Caffe and Microsoft Cognitive Toolkit, and many others, most frameworks, Paddle, they all now enable RDMA out of the box. And so this was some of the early work where you can see that this right here, right, is the ideal theoretical amount of compute that you're actually going to get out of these GPUs. This in particular is on a smaller set, ResNet 50, but you can see that as you scale out across GPUs, that you're achieving very much the linear scalability that you would expect. And keep in mind that these GPUs are very power hungry. They're like 300 watts a pop. So they're not that inexpensive. So you want to keep them busy, especially when you multiply them by 8 in a server. You want to be able to maximize the GPUs and how they're being used. So that's actually really critical. Now we've been doing a number of additional optimizations and accelerations into TensorFlow. Advanced verbs is probably not a correct word. They are the same verbs, so they're just being somewhat optimized. And basically what this really shows, and this is the latest TensorFlow 1.6, which is not on the slide, I don't think. I apologize for that. But really what this shows is, if you take the network into account and you take a look at the graph on the left here, right? If you were to run a 10 gig network, even with RDMA and all of the bells and whistles offloads that Mellanox offers, you will completely fall short of being able to maximize the throughput of what those GPUs are capable of, right? So 10 gig is just not good enough. It's just not enough, especially when you move into larger models. This in particular is VGG 16, right? And it not only exploits the benefits of RDMA in most cases, but it really shows you that the network really is a critical factor in being able to maximize the performance of the GPUs. So this is a pretty awesome slide. IBM has introduced what's called Power AI. And in their research, of course, this has all been done on Mellanox infrastructure, InfiniBand in particular. And that near linear line that would be in the perfect world, being able to maximize all the GPUs at their very peak efficiency, IBM has been able to achieve with the Power AI stack, showing 95% linear scalability. Right, so that's being able to take advantage of RDMA and the core capabilities of the Mellanox interconnect fabric. Okay, so one more last slide. I think this is another performance slide. Nickel is NVIDIA's collective communication library. They have a new version. It's called Nickel 2. And they're also enabled RDMA and GPU direct aware out of the box, and being able to show pretty awesome performance when you take a look at some of the smaller workloads as well, like ResNet 50. All right, so that puts me about 6 minutes ahead of schedule. I apologize if I went a little fast. But really what I would like to do is just maybe take a last couple of minutes and take any questions. I know you got questions.
What's the maximum message sizes that you can handle with current version of Sharp or reduce? And let's say I have 64 megabyte tensor. Would it be better for me to just sequentially run many of those small operations with maximum tensor, or just do break?
It would probably depend. So I believe the message size, I'd have to go back and check. But it's far significantly less than 64 meg even. the current implementation of Sharp, we've done a lot of testing to show performance in the current state. So for smaller messages and smaller workloads around ResNet and these types of things, it's been just as effective as maybe Nickel. Okay, but then that changes as the workload changes, right? So for VGG or much larger models, that may not always be the case. Now Q3 is when we bring out HDR. This is when it'll be generally available, and all of that current capability, like I mentioned, much larger message sizes will be supported in the HDR 200 gig devices.
Will Coral still run on both switches with the first version, or are you going to upgrade?
You would have to ask them what their plans is. So what's interesting, though, okay, because I can't comment one way or the other on the roadmap of the Coral Summit and Sierra systems, but what is interesting about the HDR devices today, in particular the Quantum switch, is 40 ports of 200 gigabits a second, okay? So today's radix with EDR 100 is 36. So then we move to a 40-port radix. Now, what's interesting is that you can split each one of those ports logically into two. Okay, so now you fundamentally have an 80-port radix for that one device, being able to do what's called HDR 100, and so it's possible that upgrades could be made. Yeah, because I know you have projects coming online in like December or something with the latest summit, right? So keep me involved. Let's make sure you're optimized. That's my goal, right? Is make sure your data is optimized.
Do you know if Nickel is planning to use Sharp as well?
So again, you'll have to wait. Now GTC is next week,
Yep.
so maybe we can talk to NVIDIA about the plans around Nickel there in offline. But it would seem like an ideal type of marriage between the two technologies. Yeah, sorry I can't just directly answer some of your questions. Only because I'm on camera.
So you mentioned the 200 gig switches. As far as the adapters that go with that, is that going to be a new adapter or an upgrade to the existing Connect X5 with boards?
So, okay, so this is a little bit more of a technical answer, but I have 2 minutes. I think I can do it. So today, EDR is 4 lanes of 25 gig, basically, right? And HDR is 4 lanes of 50. And so in order to be able to increase the radix, you use a splitter cable. So you're basically running 2 ports of 50. Now, if you try to marry a current generation EDR HCA, an endpoint, to the switch on 2 lanes, you're going to only marry 2 of them. And so fundamentally, that will actually drop your expected bandwidth even in half again, right? Now, it's quite possible to plug in a switch or to an HCA into an HDR port, and the links will negotiate at the correct speed. But when you're using the splitter technology to increase the radix, then you'll have that concern. But the core capabilities are forwards, backwards compatible. Yeah, that's one thing that's interesting about Mellanox and InfiniBand and our offloads. It's forward compatible and backwards compatible. So we're not going to break anything entirely, unless you're doing something strange like that. Then you're not. Then even all the features are there. It's just the link speed doesn't negotiate properly because you don't have all the wires there to do it. So, okay.